Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. In our previous lesson, we discussed the second law of thermodynamics in relation to heat engines. Today, we will be further exploring the relationship between the second law of thermodynamics and other mechanical objects in the universe. If you are ready, we will begin. In our last lesson, we found a new way to state the second law of thermodynamics: the complete conversion of energy from a hot source into work is not possible. We discussed how this statement can be proven using the second law. We also discussed some of the equations that help us to solve problems related to heat energy and work. Consider this statement: the spontaneous transfer of energy from a cooler body to a hotter one is not possible. Does this make sense, students? Let us do an activity. Working with a partner, try to determine whether this statement is true or not. List some examples that you think help prove the statement, and examples that contradict the statement.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. I'm sure you had fun with this activity. It is easy to think of examples that prove this statement. For instance, a bottle of ice water in a hot room does not make the room colder. There is no transfer of cold energy, only heat energy. Thus, the water gets warmer, not cooler. Imagine that you are jumping into a pool of extremely cold water that is minus 30 degrees Celsius. You will be very cold, but you will not freeze instantly. In fact, the heat energy leaves your body warming the area immediately surrounding you. Thus, your body, the system, is working to balance the temperature with the surroundings. These are two examples of how to prove the statement. But if it is true, then how does a refrigerator function? If we take a warm bottle of water and place it in the refrigerator, its temperature drops to match the surroundings. The refrigerator, however, still proves the statement, even though it appears to contradict it. The key part of our statement is spontaneous transfer. The process occurring in a refrigerator is far from spontaneous. It is instead using a heat pump, which is essentially a heat engine running in reverse. Thus, we can effectively conclude that this statement is true. The best way to understand is to compartmentalize the process. First, the objects in the refrigerator are a system. The inside of the refrigerator is their surroundings. The refrigerator icebox itself is also a system within its own room temperature surroundings. Inside every refrigerator, there is a network of pipes containing a special fluid. This fluid is called the working substance. It travels through the pipes and transfers thermal energy from inside the refrigerator to the surroundings. Initially, the liquid passes through an expansion valve. This is designed to force the liquid in the pipes to rapidly change to a gaseous state and expand. Thus, the gas is doing work, so its temperature falls. Additionally, thermal energy flows from the inside of the refrigerator into the gas. This causes the temperature inside to fall. This is in keeping with the second law, since the gas is much colder than the inside of the refrigerator. Work is then done on the gas in order to compress it and turn it back into a liquid. This is the input work for the system, which causes an increase in the fluid's temperature. The fluid then passes through several more pipes on the back of the refrigerator. Since it is now hotter than its surroundings, its thermal energy is transmitted to the space surrounding the refrigerator. This transfer is the output work of the system. This is an example of a cyclic process. The liquid will once again travel up the refrigerator to the expansion valve, and the process begins anew. In the case of the refrigerator, work goes into the heat pump and allows energy to flow from a colder region to a hotter one. In this case, there is more work done on the system than by the system. This can be written in the form of an equation to satisfy the second law of thermodynamics. Energy into a hotter region, or heat reservoir, is equal to input work plus energy from the colder region, the cold reservoir. This can be written as QH equals W in plus QC. This formula can help to determine the coefficient of performance K of a refrigerator. It is the ratio of change in heat at the output to the supplied work. The formula reads, coefficient of cooling performance is equal to the ratio of heat removed from the cold reservoir over input work. Students, let us do another activity. You will be provided with two schematics. Determine what the schematics are for and label all the bodies and indicators. You may begin.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I am sure this was not too difficult. The first schematic is that of a basic heat pump. To start, the three bodies are the heat source, the cold reservoir, and the system. The arrow entering the system is the input work. The arrow coming from the cold reservoir is the energy transferred from the cold region. Leaving the system is the energy transferred to the hotter region. The second schematic is that of a basic heat engine. The three bodies in the schematic can be identified as the heat source or reservoir, the system, and the heat sink. The forked arrow in the schematic needs to be labeled 3 times. At the source, the arrow is labeled as the heat transfer from the hotter region. The smaller branch of the fork traveling to the heat sink is the energy transfer to the cold sink. And the arrow leaving the system is the work done, or output work. Were you able to label each correctly? If so, great work. This concludes today's lesson. We have discussed the relationship between the second law of thermodynamics and the functions of refrigerators and heat pumps. Until next time, thank you, teacher. Thank you, students.